Okay, I think we'll go ahead and get started. How's everybody doing this morning? Very good. Yeah. Monday morning, 8:30, at 11. So what we'll do today is we're going to finish off chapter 1. Hold on a second. We're going to finish off chapter 1 today, and then we'll start on chapter 2. And remember, we were going to have a quiz today, but that's been moved to Wednesday. So the quiz will only cover chapter 1. So even though we're going to be doing some chapter 2 today, it won't be on the quiz. And I'll talk a little bit more about the quiz once we finish chapter 1, just to give you a feel for how it's going to work. So let's talk a little bit about significant figures. When we talk about significant figures, the idea behind that is when we have our data, we want the numbers that make up that data to be as accurate and as informative as possible. And so based on how the measurements are made, how the calculations are done, our calculator or our spreadsheet may give us a whole bunch of digits. You know, if you think about your calculator, you do some addition or multiplication or subtraction or something like that, you usually get a lot of digits. Well, from a math perspective, that's correct, but from a value of the data perspective, a lot of those digits really don't have any meaning based on how we did the measurements. So we talked before about, remember when we measure the quarter, and depending upon what kind of ruler we had more confidence in some of the numbers than the others. So significant figures are always the numbers that we're totally certain of based on our measurement, and then the one number that we have a pretty good idea about, but we're not quite as certain. And so we're going to talk about how we do that a little bit today. When we do calculations, we want to suppress that urge to write down all the digits that our calculator or our spreadsheet gives us, okay? Once again, we do that because all those digits aren't significant. They're not really reflective of the type of measurement we did. So just some of the rules about significant figures. All non-zero digits are significant when we have the number. Zeros between the non-zero digits are significant. Zeros at the beginning of a number are never significant. Zeros at the end of the number can be significant if it contains a decimal point. And then finally, how about whole numbers ending in zeros? So whole numbers ending in zeros aren't significant unless you have that decimal there. So here's a few examples of significant figures. So we look at the first one, 1.03 times 10 to the 4th grams. There we have 3 significant figures. So why is the 0 significant in this one? Any thoughts on that?
In between the non-zeros?
Right, it's in between the non-zeros. So that's that rule number 2 that we had. And then 1.030 times 10 to the 4th, we're saying that has 4 significant figures. Why is that last 0 significant? Well, it's because...
The decimal?
Pardon, go ahead, yes?
Because it contains the decimal?
Right, it's after that decimal, because of that decimal. And remember, we talked about scientific notation and one reason why you would use that. This is a good example of it. In fact, both of these last 2 are good examples of where we want to make sure that we show that those zeros at the end are significant. And an easy way to do that is by using scientific notation. So then the last one, 1.0300 times 10 to the 4th grams, we say that has 5 significant figures. So both of those zeros at the end are significant in this case. And we can reflect that easily by using scientific notation. So it's essentially the same number in each case, right? It's 1.03, but we have some of those zeros on there. What would that be an indication of? Why do you think we had more significant figures in those next two than the first one? Any ideas? Yeah.
Extra degree of precision.
Extra degree of precision, extra degree of accuracy, I would call it more. Because remember, what's the difference between precision and accuracy? Does anyone remember that from last class? If I say my measurement was very precise, that means that I did multiple measurements and I got pretty close to the same answer every time. It doesn't necessarily mean that it was accurate. Accuracy is how close I am to what is the true or known value. So what this is telling me, and you'll see this, think about, not certain who everyone had for the lab, but I know in my two lab sections, one thing I pointed out was the balances over by the windows in the lab. Does anybody remember seeing those balances when you were in there? And there were two types of balances. If you're facing the windows, the ones on the left, I think there were 4 of them, they're kind of shorter, flatter balances. And then I think there were 3 up on the right that were a little bit, had like a glass case around the part. Well, the short, flat ones are top loading balances. The other ones are analytical balances. The top loading balances in that lab only have, you only can weigh to 3 digits past the decimal. Okay. The analytical balances, you get an extra decimal, you get a 4th decimal place. So this is an example of where if you use the analytical balance, you'd be getting more significant figures because you'd be getting that additional digit on your weight versus the top loading balance. So that would be an example of how you could do the same measurement, but yet get different numbers of significant figures when you start working with the data. And remember we said before that we want the significant figures to reflect the accuracy of our measurement. Well, if we use that top loading balance and only got 3 digits past the decimal, and then we got the analytical balance and got 4 digits past the decimal, then we definitely would have a little bit more accuracy with that analytical. And you can say, does it matter? Well, sometimes it does, sometimes it doesn't. Kind of depends on the measurement you're doing and what you're going to do with the data. Okay, so let's look at a couple examples here. Again, how many significant figures do we have for each of these? The first one, 0.035, 0.00305. How many there?
3.
3, right. 1.00. 3 again, because we have those zeros past the decimal. 100. Just the 1, because if I would have put a decimal after that last 0, what would it have been? Then it would have been 3, but because we didn't put a decimal there. 0.10556. 5, right, because that 0 is wedged in between a couple of non-zero digits. And then finally, 2.050 times 10 to the 3rd. 4. That last 0 is significant because of it being past the decimal. So does everyone kind of get a feel for the significant figure stuff? So we have just kind of understanding the rules around significant figures that we just talked a little bit about. Well, where this is going to come into play is usually you don't just have one number like that and are trying to figure out the significant figures. Usually you're in a situation where you have a series of measurements that you're using, and then you're using those numbers to do some type of calculation to get your answer. And really what you're after at the end of the day is what is the significance of that final answer. And so you're interested in figuring out what's the significant figures in that final answer. And usually you don't have the same number of significant figures in all the data that you're using. So you have to make some judgment, you have to make some decisions on how you do that. The least certain measurement limits the number of significant figures in the answer. So if you have, say, 4 or 5 pieces of data that you're using in your calculation, and they have different amounts of significant figures in each of those measurements, you pick out the one that has the smallest number of significant figures, and that's going to be the driver for your final answer. Now, the one thing I will say is that typically the way you do it is, because anymore everyone's doing a spreadsheet for most calculations, is you go ahead and let the calculation just run, and then you do your rounding at the end. That's the most common way to do it in terms of getting to the correct number of significant figures. The other thing is when you're doing adding or subtracting, the answers are rounded to the least significant decimal point. So in other words, if you have one number, say, let's go to that balance example. If you had two weighings that you did, and one sample was weighed on that analytical balance, and you had 4 digits past the decimal, the other weighing was done on that top loading balance where you had 3 digits past the decimal, and then you wanted to either add or subtract those 2 numbers, your final rounding, would it have the 3 digits or the 4 digits past the decimal? It would have the 3, right, because that's the least, has the least number of digits past that decimal. So that will drive the number of significant figures that you have. We've talked about this, multiplication and division. It's the fewest number, the measurement that has the fewest number of significant figures is the driver for that. And then finally, as I said before, you want to be cognizant of the number of digits that you're going to be working with at the end as you go through the calculations, but you don't do that rounding on each step. You go ahead and do the calculation through, and then at the end, then go ahead and adjust for the proper number of significant figures. So I guarantee you will have to make some kind of decision like this on the quiz, where you'll do some calculation, and then you'll have to determine what the appropriate number of significant figures are, in addition to what obviously the correct answer is. And the significant figure stuff should also carry over into when you do your laboratory experiments in the lab. So when you report that data. So I think I can speak for the other instructors as well. If you do some measurements and you have, say, 4 significant figures in those measurements, and then you report an answer out with 8 digits, you're going to lose some points on that. And that's really the key thing with the significant figures, as I've said a couple times already, is we're trying to get the answer to really reflect the accuracy of those measurements. Okay, so let's look at a couple examples here. So in this first one, unless you're really good at math, you probably can't do that in your head. I know I can't. But how many significant figures would you report that to, the first one? How many? 3, right. Because that 24.6 with the 3 is the one that's going to drive the number of significant figures there. Does that calculation look familiar to anyone on something? Why would you, what's grams per mil? Does anyone remember what that is? Yeah.
Dimensional analysis?
Well, we're doing dimensional analysis, but if I say something is 1.0567 grams per mil, what am I probably talking about based on what we looked at in chapter 1? Does anyone remember grams per mil? Go ahead, yes?
Wasn't it density?
It was density, very good. Remember we said density is weight per volume. So this is an example of dimensional analysis where you can imagine the question saying something like, you had 24.6 mils of some substance, and its density was this 1.0567, how many grams did you have? So we see the mils, cancel the mils, and our answer is in grams. So the answer would be 24.6 mils was equal to 26 grams. The next one, we're doing a subtraction here, 4.6389 minus 2.1. How many significant figures are we going to have on that one? Did I hear 4?
2.
2, okay, yeah, because we said, once again, that addition and subtraction, what drives it there is whichever one has the least number of digits past that decimal point. In this case, the 2.1 just has the 1 digit. And then finally, the last example here, 25.6 mils plus 27.81 mils. That's going to be similar to the one we just did because the 25.6 mils with the 1 digit will drive the significant figures in our final answer. So these are examples of typical calculations that you would do where you take some of those significant figure rules that we talked about and then apply them to get our answer at the end.
I have a question.
Yep.
So when you have multiple, like say you multiply 2 numbers and then you add it to a number,
Mm-hmm.
what do we do with significant figures there?
So the driver is going to be in what you just described. So you do your multiplication and you would get some kind of answer, right?
Mm-hmm.
Then you would go and do the addition or subtraction or whatever. It would be that combination of what were the significant figures on that first multiplication, okay? So you have to be cognizant of that. If you had, say, 4 significant figures that come out of that, and none of them are past the decimal, and then you're trying to subtract, say, like 1.1, then you would not have any significant figures past that decimal point. Because you would have, in that case, you'd be adding or subtracting one number that had nothing past the decimal and another number that had one thing, so it would be the least one. So what you have to do is you have to just kind of, even though in your calculation you're not rounding, you still have to be cognizant of each one of how many digits that you're dealing with.
Okay.
Does that make any sense?
Yeah.
Okay. So the other thing I'll say about significant figures is some instructors are real sticklers for it. For me personally, if I think you made a reasonable effort at figuring it out, I'm okay with that. What I don't like to see is I don't like to see you getting, say, using your calculator and getting 8 digits past the decimal and then reporting all those digits when nowhere in your data do you have something that indicates you have that many significant figures. If it's 2 versus 3 significant figures or something like that, that doesn't bother me too much because a lot of the significant figure stuff, people get in arguments about this of how you handle it and things like that. And I'll be honest with you, years ago when spreadsheets started being popular to do your calculations, and yes, there was a time when there were no spreadsheets, believe it or not, there was a lot of discussion about that. Because where people get tricked on that is they'll tell Excel, for instance, to only show, say, 3 decimal places or something like that. What you don't realize is that's just what you're seeing. Excel is still using all those digits for the calculation. So some of the nitty-gritty stuff like that can be a little subjective. So for me, what I'm looking for is, so just going back to this. So like take the first one, for instance, where it's 24.6 times 1. If you did the math with your calculator or your spreadsheet, you get a whole bunch of digits. I just wouldn't want to see a whole bunch of digits. I want to see an effort to show me that you're at least thinking about significant figures, okay? I'm not speaking for other instructors, I'm just speaking for myself. Okay, dimensional analysis. So we've been talking about this for a while, and we've had some examples of it, whether we realize it or not. let's just talk about this a little bit more, just because this is something that you're going to be doing over and over and over to the point of where you won't even realize that you're doing it anymore. It just becomes second nature. Dimensional analysis is simply how we use conversion factors to switch from one type of unit to another. And what we'll find is that a lot of the formulas and things like that require the different variables to be in a particular unit. And so you may do a measurement in something grams, but it really needs to be in kilograms. So you need to understand how to switch from grams to kilograms or vice versa. You may measure something in milliliters, but the equation requires it to be in liters. So you need to learn how to do those conversions. That's what we're talking about in dimensional analysis, is how do you do these conversions? And one of the key things to it, and I think I mentioned this before, but I'll mention it again, is writing the units and seeing if your units cancel. If your units aren't canceling out, then you don't have the problem set up correctly and you're going to get the incorrect answer. If you have the units set up properly so they're canceling out to get to that unit that you want to end with, then it really increases your chances of getting the right answer. Then it's a matter of, did you do the calculation correctly? And most people can do that. It's in that setting up of the problem that people get stumped usually. So we use this ratio to change units. So we have something in a numerator, we put something in a denominator, and the next ratio to cancel out. That converts it to whatever was in that numerator, and then on you go from there. So in the example below, there's a couple of them in a row. It's not uncommon to have multiple conversions. You'll see that more as we get along in the semester. That's pretty normal to do stuff like that. And in this example below, they're just showing how you would go from meters to inches, using the conversion factor for meters to centimeter and then centimeter to inch to get that change in units from meters to inches. So that basic idea, whether it's something like this where it's just a length measurement that you're converting, whether it's weight, whether it's volume, whether it's whatever, is the same basic idea of using dimensional analysis by lining up those units in the numerator and denominator appropriately so that things cancel out, and then you wind up with the right unit in your answer. So I think in the homework problems, there are some dimensional analysis things. So I really encourage you to work a few of those so that you get comfortable with it. Let's look at an example of dimensional analysis here. So we're saying that sound travels at a speed of 768 miles per hour. So then how many miles does sound travel in 1 week? So what's the main conversion that we're trying to do here? Anyone have any thoughts on that? I'm sorry, what was it?
Time.
Time. And so we're trying to convert hours to weeks, right? To a week. So if we say there's 24 hours in a day and 7 days a week, we've converted that hour, that denominator, into weeks. And so now we've gone from miles per hour to miles per week. And if we look at this, we see that our things cancel in a way that hour, 1 hour go into 24 hours per day, days per week, and then finally, how many hours in a week, basically, is what we're getting to. And then divide that into 768. So does everyone see there how the units cancel? Okay. So here's a list of some homework problems I suggest you take a look at and try and work through. It'll give you a little more practice on the dimensional analysis and significant figures and some of the other things we talked about. Just to remind everyone, the slides are posted in Canvas, and the homework is posted as well in Canvas. And so these all have the answers in the back of the book. As I said before, I don't collect the homework. I don't check the homework. That's up to you if you want to do it or not. It's just a good suggestion to kind of give you some practice for the type of stuff you'll see going forward. Okay, so that completes chapter 1. So if you think about some of the stuff that we did in chapter 1, there's some calculations to learn, like the density calculation and some things like that. There's dimensional analysis and significant figures that we talked about, kind of getting comfortable with how you do dimensional analysis, how you adjust for significant figures, things like that. But the reality is that a lot of the stuff in chapter 1 are things you need to go back and memorize. We talked about some of the definitions on the scientific method in the beginning, theory and stuff like that. We talked about intensive, extensive properties. We talked about elements, how are they named? And so memorizing some of those element names. So carbon is C, iron is Fe, things like that. So there's a fair amount of stuff to memorize. Some of the prefixes, so like mega, milli, things like that, remember those. So the expectation is that you'll go back, you'll memorize some of this stuff, and then you'll also get comfortable with some of these calculations that we did talk about. So that's the kind of stuff that would be on the quiz and then also on the first exam when we have that. Any questions right now before I tell you a little bit more about the quiz?
How did you get the 1.29 and the last answer?
Okay, well, I'm sorry, what was that again?
How did you get the answer 1.29 in that last question we did?
Okay. It should be, if you do 768 times 24 times 7, it should be 1.29 times 10 to the 5th.
Okay, thank you.
Okay. I hope it's right. I think it is. Okay, so to talk about the quiz for a second. So the quiz will be on chapter 1 only, and that'll be this Wednesday. It'll have 15 questions, each worth 2 points. The way the quiz is given is you'll have a 15-minute time limit to do the quiz. Remember, I talked about this before, that since everyone's kind of on the honor system taking this, it's open book, open notes, all that. So to kind of manage so people just don't look everything up, there's a time limitation. So when you go into Canvas where the quiz will be, and once you open up the quiz, the clock starts ticking and you have 15 minutes. If you have a reasonable idea of what you're doing, 15 minutes is plenty of time. There will be about an hour window that you can take the quiz in, and that'll be listed in Canvas as well. The plan is on Wednesday that we will cut the lecture portion short so people will have plenty of time in this class time period to take the quiz. So my preference is that everyone should just take the quiz during the class time. For those of you who are here in person on Wednesday, you can certainly bring your book or your computer or something like that. That's perfectly fine. And for those of you who are remote, obviously just be set up to take the quiz however you're comfortable. So that's how it'll go. You know, typically this isn't how the quizzes are given for me, because usually I just pass them out and let the students take it. So hopefully everything goes as planned. So far, we've been pretty successful with the technology, so I'm optimistic on this. So any questions on how that quiz is being given or about the quiz in general? Okay, great. All right, so let me switch over to chapter 2 here. Give me a moment. Okay. So in chapter 2, we're going to start talking about atoms, molecules, and ions. The first part of the chapter is kind of like a chemistry history lesson. And so we're going to go through it, and the main idea through kind of going through this part is to just kind of give you a feel that for some of the stuff, when it was developed and kind of just a little bit of the process that people went through. It's kind of interesting when you, at least to me it is, that a lot of the stuff that they talk about, you look at it now and you kind of go, well, yeah, everybody knows that. And so you just need to put it in the context of when these people were discovering this stuff and figuring this stuff out, it was a pretty big deal because it was pretty controversial at the time. A lot of discussion in the scientific world about is that right or is that not? And it's like most things that once things are known and you move along in time, then it just becomes second nature to everyone. And I think we kind of lose a little bit of the appreciation for it. So the stuff that we'll talk about in the beginning, in terms of like, will you use it later on in chemistry and that? Probably not. It's more like I said, a history thing, so you get an appreciation of how some of these theories developed and some of the things that had to be done to get there. And so now when we look at it, we tend to take it for granted a little bit, but at the time it was really pretty amazing that people could figure this stuff out, especially when you think of the fact that back then, a lot of the technology like computers and things like that we depend on, they didn't have. So when you start talking about atomic theory of matter, it goes all the way back to the Greeks. And there were some philosophers that said that all of nature was made up of some small particle. And that's really where the word atom comes from. And that means in Greek, I guess, uncuttable. And so, and you think about that, that's some person philosophizing that years and years and years ago. And that basic idea was right, is that things are made up of atoms. Okay, and that held up. So pretty amazing if you think about it. In the 18th and 19th century, there was a guy named John Dalton in the 1800s who took some of the laws that had been figured out and kind of pieced them together to come up with his idea of atomic theory. So was he right on everything? No, we'll find out. We'll see that he wasn't right on everything, but he had a pretty good idea on some of the things. And it served kind of on that first stepping stone basis for future things, for people to figure things out a little bit more. One thing, and you may know this already, but one thing about science is rarely does someone figure something out and it's right the first time. Usually what happens is someone figures something out and it's got a lot of right elements to it, but it's not got everything figured out. And then people come along and take that information and expand upon it to get kind of those final theories. And so it's kind of an evolution of things. And so 3 things that he depended on and pieced together. One was the law of constant composition, the law of conservation of mass, and the law of multiple proportions. We've talked about constant composition a little bit, but we'll go over that again and we'll go over the other 2. So does anyone remember what this constant composition or law was? Well, we said that if you have a particular compound, and let's take water for an instance, we all know water is H2O. And what we said is, this law tells us that if it's water, it's H2O, whether it's in St. Louis or Webster Groves or California or New York or Europe or wherever. Water's water, okay? And so that any sample of that, of a compound, will have the same proportions of the constituent elements. So that's the law of constant composition. Law of conservation of mass tells us that when you have a chemical reaction, the total mass stays the same. So in other words, you don't create mass, you don't lose mass. Now the mass changes, but if you add up, say you burn something, okay? You have the material that you started burning, and that material goes away. It becomes ashes, or it volatilizes or whatever. But if you captured all that stuff and counted the carbon atoms that you started with, and counted the carbon atoms in all these reaction products, the number of carbon atoms would be the same. So this is this idea that matter is neither created nor destroyed in a chemical reaction. Like I said, it changes, the composition changes, the molecules change, but the number of those atoms that you started with and the atoms that you started with, that remains the same. So that's the idea of conservation of mass. And then finally, the third one that he used to develop his theory is law of multiple proportions. So what this means is if you had two elements, A and B, and you combine them in some number of A and some number of B to get a final compound, the ratio of A to B are always whole numbers. So going back to the water example, we always say H2O. It's never H, one H, a half of an O. So in other words, you can't have half an O. It has to be a whole O. So then it becomes H2O. And so that's what this is saying, is that it always is, the ratios in that molecule are always whole numbers. It's never half a number or something like that. Okay? So those three things that he used to develop his theory, and we'll talk about his theory in a moment here, are things that we really take for granted in chemistry on a daily basis. And it's amazing that many years ago, they were able to figure that out, and it's held up this long. So let's talk about his theory a little bit. So his theory says that each element is composed of extremely small particles called atoms. It also says that all atoms of a given element are identical to each other in mass and other properties. But atoms from one element to another, there are differences. And so what all this is telling us is every hydrogen atom is the same. Every oxygen atom is the same. Every carbon atom is the same as the other ones. But the hydrogen atom is going to be different than the carbon atom, which is going to be different than the oxygen atom. And so, once again, the key thing to kind of have as a basis. And then atoms of an element are not changed to atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. So this goes back to the one law that we talked about, of where you do a reaction and how the atoms are assembled together may change, but the fundamental atoms don't. So you're not taking a carbon atom and converting it to something else. It's still a carbon atom. Atoms of more than one element combine to form compounds, and a given compound always has the same relative number and kind of atoms. This is that kind of related to that definite proportions thing. of where, as I said before, water is always H2O, things like that, of where once we know that molecular formula for the compound, it's always that, if it is that compound. If it's not that, it's something else. So, not bad, okay? So Dalton's attempt to explain atomic theory, to explain atoms and all this, was pretty good. Except there was one kind of flaw in his thinking, a major flaw. And that is, he thought that the atom was the smallest particle possible. Okay? Well, as we know now, that's not exactly correct. So that the atom itself actually is made up of even smaller particles. And this is where we're talking about protons, neutrons, electrons, things like that. And these smaller particles are known as subatomic particles. So subatomic just means smaller than an atom. And so we're going to talk a little bit about electrons and how that was discovered through cathode rays, radioactivity, and then also nucleus, the nucleus of the atom with the protons and neutrons. Okay, so one of the things that was done early on, and this is a guy named Thomson back in 1897, is he discovered the electron. And so they had this thing called a cathode ray tube. And so the cathode ray is just another word for electrons. And so what he found is, if you had a fluorescence target there, you could actually see the electrons, because when they interacted with the fluorescence background, you can kind of see the white light on there a little bit in the tube. That's what they're talking about. And so in this case, the cathode is the negative side, the anode is the positive side. We said before that opposites attract, right? And same charge repels. So the electrons, because they're negatively charged, and just remember, they didn't know this at the time that they were negatively charged, but because they're negatively charged, they'll move from that cathode. Remember, negative charge repulsed by the negative wants to move towards the opposite. The anode in this case is plus. It'll move across, and with that fluorescent background, you can see the things going across. The other interesting thing is, you see in the second picture, the person is holding up a magnet, and you see the kind of light line bend a little bit. So if you put these things in a magnetic field, you can cause them to move a little. There's a bunch of chemistry stuff in the world of analytical chemistry, mainly mass spectrometry, that's based on moving electrons, moving ions in general this way, using charge and using magnetic fields. We'll talk a tiny, tiny bit about it, but once again, if you take instrumental analysis next semester, in a few years, then we'll talk about it a lot more. So a really neat discovery, but it was one of the things when this was discovered that talked about how, okay, that initial theory, there's some weaknesses in it, some flaws in it. Once again, this is just showing, again, the charged plates there, the path of the electrons, a fluorescent screen where you can see it, and a magnet there. Wouldn't worry too much about the details of this. The key takeaway is that through this work, they learned that there are negatively charged particles present. And those negatively charged particles we call electrons. The other thing that he did is he measured the charge to mass ratio of the electron to be 1.76 times 10 to the 8 coulombs per gram. Why was that important? That was important because if you knew what that ratio was, then all you needed to do was then either determine either the charge or the mass, and then you would get the other. Because remember, he had the ratio, but he didn't have the charge and he didn't have the mass. He didn't know if the charge was 2, 3, 4, or some other number. And that. So this guy Millikan did this, what they call the oil drop experiment. There's a little bit of detail on that, but basically the takeaway for this that I want you to remember is Millikan was able to figure out that an electron is negatively charged. So once again, another early 1900s type thing that happened. Let's talk about radioactivity a little bit. So radioactivity is defined as the spontaneous emission of high energy radiation from an atom. There's a picture of Marie Curie. I think most people have heard of her. Her and her husband did a lot of work on this stuff. But what this whole radioactivity stuff did was it showed that atoms had more subatomic particles and energy associated with it. So we've talked about the electron a little bit. Let's talk about what came out of the radioactivity work. So there's a guy named Rutherford who did some work, and he found 3 types of radiation associated with this. One are alpha particles, which are positively charged, beta particles, which are negatively charged, kind of like electrons, and then finally gamma rays, which are uncharged. You see another kind of common theme here at the bottom of where they use electric fields, in this place, electrically charged plates to kind of bend stuff. The stuff will bend up in this example if it's negatively charged. Once again, opposites attract. If there's no charge, it just goes straight through. If it's positively charged, it'll go down towards the negative plate. So the key thing I want to point out on this table is when it comes to radioactive type stuff, there's 2 things you're concerned about. One is ionizing power, and that's the ability of radiation to create ions. So in other words, if you use the radiation to bombard something, you can create ions. The other is penetrating power. And penetrating power is the ability to pass through material. And so where a lot of this comes into play is when you think of some of the medical stuff, is that gamma radiation, which is the 3rd one here in the table, high energy photon, and we see low ionizing power, high penetrating power. That's used in the medical stuff because you don't want a lot of ionization going on because you don't want stuff in your body being ionized, right? That might cause problems. But the penetrating power, that allows you to kind of look in things and get penetration through and see things in the body. So alpha is high ionizing power, low penetrating power. Beta is moderate for each of those. And then gamma is the low ionizing, high penetrating.
So is that what they use for X-rays?
Yeah. And that's why, so like I went to the dentist last week, right? And they did the X-rays of the mouth. They put that big lead thing on you. That's why, it's to protect you from the energy. So it just goes to your face in that case. Because even though it's low, it's still, low is a relative term. It's still not a good thing. And so that's why, I mean, X-rays are kind of limited in what they can show. And MRI is actually, for certain things, a lot better because it's a totally different process of how it works. But the MRI also doesn't have all that negative, it doesn't have the ionizing part based on how it works. Okay, let's just talk about these briefly. So alpha radiation is composed of particles consisting of 2 protons and 2 neutrons. And you see over there on the far right, it's usually represented by the helium nucleus. And once again, high ionizing power, low penetrating power. Beta radiation, kind of in the middle. It's a smaller particle, so it is more penetrating. In general, the smaller the particle, the more penetrating it is. In beta decay, a neutron converts to a proton, emitting an electron and increasing the atomic number by 1. So that's the one that's similar. We see here with the negative charge, that's similar to an electron. The gamma radiation is a little different than the other 2. because they're electromagnetic radiation, they're not actual matter. And this has the highest penetrating power, lowest ionizing power. And so there's an example of cesium-137. It's a gamma emitter, and it's used in cancer treatment. So in the early 1900s, there was another, based on a lot of this stuff that was learned, there was another kind of theory that came out by J.J. Thomson, and he kind of considered what the atom was kind of like a blob of pudding, a ball of pudding, and had negative electrons embedded in it. So he thought it was this big sphere of positive charge with some negative charge electrons stuck in it. I guess that was good at the time. Seems kind of goofy now, but all right. I think most people like pudding, so that's a good thing. So then a guy named Ernst Rutherford did some scattering experiments. So in other words, he had some gold foil, he shot particles at it, and then using this fluorescence screen around it, saw what he expected to be, he would see the particles come through. The expectation is that the particles would just pass through if this kind of pudding idea was correct. Well, what they noticed was most of the energy came straight through, but some of it deflected off the sides. And so it's kind of like, just think of it, if you were rolling a ball down a bowling alley and you had the pins lined up where the ball could fit between them without touching it. Well, if you threw it straight through and there was enough space there, it would always go straight through and it never hit anything. But then if you start throwing that ball and it hits a pin and the ball deflects to the side, that's what they saw there. So there had to be something in there that was causing it to deflect. Well, what was it? That's where they decided there must be some type of nucleus to the atom. And so there you see the alpha particles coming in. So they've leveraged some of this stuff they learned about radioactivity to shoot alpha particles in. Usually it passes through, it would miss that nucleus because the nucleus is pretty small, but every so often it would hit a nucleus and then scatter off to the side. So this Rutherford scatter type thing is used in other areas of chemistry, but it was a really important thing to find out here when they were developing this nuclear theory. So what he decided was that there had to be a really small, dense population in the nucleus that was causing this scatter. He also theorized that most of the atom space is just that, it's space, it's not stuff, it's not matter. And so atoms are really small. So 1 to 5 angstroms. An angstrom is 10 to the minus 10th meters. So 1 to 5 angstroms. If you look at the nucleus, though, the nucleus is about 10 to the minus 4 angstroms. So atom itself is small, the nucleus is even smaller, and this explained how you could shoot that radiation through and not get any scatter. The other subatomic particles, protons and neutrons, are located in that nucleus. Some of the things that were discovered is that the charge of an electron is minus 1.602 times to the minus 19. The charge of a proton is just the positive of that. That quantity is called electronic charge. We rarely talk about it with those numbers because a long time ago it was determined that you would use multiples of this. So when you talk about charge, you usually talk about +1 or -1 or something like that. You don't say the Coulomb number. Neutrons are neutral, so there's no charge with those. So electrons are negative, protons are positive, neutrons have no charge. Every atom has an equal number of electrons and protons so that the atom has a net 0 electrical charge. So if you have five protons, you're going to have 5 neutrons, or rather 5 electrons, so that you have a net 0. So just repeat that again. The electrons and protons are equal so that you have a net 0 charge for the atom. And then as I said before, an angstrom is 10 to the minus 10th meters. And that's really how people talk when they talk about dimensions of this stuff. It's always angstroms. So when we talk about the mass, remember we showed the picture of that big space. We said most of the outer space is just void. The electrons are moving around there. The reason for that is the electrons have a very small amount of mass. If we look at the bottom, we see that the protons and neutrons, remember the proton is the positively charged particle, neutron is the neutral particle, electron's a negative. We see that the proton and neutron are pretty much the same mass, okay? We see the electron is much smaller mass. And not only is it smaller, it's a lot smaller in terms of mass. So we'll talk a little bit about atomic masses. That atomic mass is simply the sum of the protons and the neutrons. We don't really count the electrons because they're so much smaller than those other 2 particles. So we also said that the nucleus has the proton and the neutrons in it. So that nucleus accounts for the bulk of the mass. Now the electrons going around it make up the volume, so to speak, but the mass is all dependent upon those protons and neutrons.
So you said the protons are in the nucleus?
Yes. Okay. Protons and neutrons are in the nucleus, and then the electrons are kind of that cloud that's around the nucleus. And the nucleus is the thing when they shot that beam and they got the scatter, that's what it would hit. And that's how they figured out there was a nucleus, that there was something there. And then they wound up calling it the nucleus. So when we talk about elements, every element has an atomic number assigned to it. The atomic number is simply the number of protons in the nucleus of the atom. Remember, we said that the atoms will have a net 0 charge. So if the atomic number is telling us that's the number of protons, then there has to be the same number of electrons present to balance out that charge so we get a net 0 charge. So we'll talk about the periodic table here in a few moments. So on that periodic table, every element has an atomic number associated with it. That atomic number is telling us how many protons are there. And by association, how many electrons as well. You'll often see elements written like this, where in this case, we're looking at carbon. So the C, the capital C, that's the symbol for carbon. That's something we're all going to learn for our quiz on Wednesday. And then the superscript to the left of the carbon, the 12 in this case, that's the mass number. So atomic mass is the sum of protons and neutrons. Because remember we said electrons don't really contribute to that mass because their number is so much smaller, whereas protons and neutrons have about the same mass. So mass comes from protons and neutrons. We kind of ignore the electrons there because it's a very small number. And then the atomic number in this subscript here on the left of the C, in this case it's 6. That atomic number tells us how many protons are in carbon. So it also tells us the number of electrons, because to get that charge to balance, so if we've got protons, remember, are plus, so we got 6 pluses. To get a net zero, we'd have to have 6 minuses, so that'd be 6 electrons. So in carbon, how many neutrons do we have? 6, right. Because if 12 is the number of protons plus neutrons, and the atomic number tells us there's 6 protons, 12 minus 6 is 6. So once again, from our initial periodic table learnings, we know that the elements are always represented by this capital letter. Sometimes it's 1 letter, sometimes it's 2. If it's 2, the second number will not be capitalized. And in this case, carbon was the example. We see that superscript, the 12, is the mass number, and mass is protons plus neutrons. And then the subscript, in this case 6, tells us the atomic number, which is the number of protons, and when it's neutral, the electrons also. So this is something, then we can get the number of neutrons by doing that subtraction of the atomic number from the mass number. So this is something when we get to tests and stuff, quizzes on chapter 2, this would be the kind of thing you would be expected to know. Okay, so in the world of elements, there's something called isotopes. And isotopes simply mean it's an atom, but it has a different mass. So if an atom has a different mass, what would have changed? Any thoughts on that?
Number of neutrons.
Number of neutrons. Because we said before that if it's a particular element, that the protons don't change. The protons are always the same. So here they have the example of carbon and some of the isotopes of carbon. And carbon-12 is the most common one. That's the normal one. Carbon-13 is the one you hear about when you hear like archaeology stuff, and they'll talk about carbon dating and that. They use carbon-13 because it's a radio-labeled thing. And so, but what you notice is, and here they have 11, 12, 13, 14. Those are the 4 isotopes of carbon. They all have 6 protons. That doesn't change. They all have 6 electrons. That doesn't change. Whether it's carbon or anything else, the protons and electrons don't change to get those isotopes. What changes is the mass, and that means the only way to change the mass, if we're holding the protons constant, is to change the number of neutrons. So there you see in carbon-12, the one we were talking about, you have 6 neutrons. You go to 13, now you have 7. So by varying that number of neutrons, you get different weights, so to speak, and that's how you see the different isotopes. You see the little footnote at the bottom that says about 99% of carbon that's found in nature is the carbon-12. So the other carbons aren't seen very often, but they are present. So the mass of an atom, as you can imagine, is really little, the total mass. The heaviest known one is 4 times 10 to the minus 22nd grams. So like a lot of these things, we don't like talking in these unusual type numbers. So there's a mass scale that's used where 1 atomic mass unit, which is what ANU stands for, is equal to 1.66054 times 10 to the minus 24 grams. So we're not going to be talking about 10 to the minus 22nd grams or 10 to the minus 24th grams, whatever. We'll be going with atomic mass unit. So if we think back a moment to our carbon example, we saw that we saw that there were 4 different isotopes. So if someone were to ask you, what's the molecular weight of a compound where you've got all of these different atoms in there, and you're going to be adding them up to get that molecular weight. Well, which number do you use? We had 4 different numbers there. What's done is, to get the atomic weight of carbon or any other atom, is you take into account what the relative abundance is of each of those isotopes, and then the mass associated with the isotope, and then sum up that to get the atomic weight. So here, the third bullet is the formula. So you have the atomic mass. So if we take the carbon example, carbon 12 would be 12 times 0.99, is 99%, and then plus whatever the other one, like, I don't know what those are off the top of my head, but whatever carbon 13 is, it would be 13 times, let's just say it's 0.5, times 0.5, and on down the line. And so you sum up those masses, and that comes out to be the atomic weight that you'll use. So it's kind of that average. The scale in general is based off of carbon 12. Carbon 12 is defined as being exactly 12. So once again, this is just in the measurement world, coming to agreement, this is how it's going to be done. Remember before we were talking about, in some of that early work, how they use magnetic fields and charged plates and things like that to move ions around? Well, there's something in the world of chemistry called mass spectrometry. And so here's an example of one type of mass spectrometer where you can go ahead and you can determine these ratios of these isotopes. And so this is one thing that you do in mass spec all the time, is you'll see over on the right-hand side there, you see where it says signal intensity and atomic mass. And you can actually separate out the isotopes using that. In this particular instrument, like I said, there's some different variations off this. You have a magnetic field. That magnetic field accelerates the ions through. The magnet then kind of bends it. Remember, we had that early example of where the ions were going through and you held up the little magnet and it caused it to bend. This instrument is doing that. And then based on that, it allows you to separate out the isotopes. So we're not going to worry about this too much, but this is just an example of one way to do this type of work. So the periodic table, we're back to our old friend periodic table. And so this is just our arrangement of the elements in order of their atomic number. And when you arrange them according to their atomic number, as you'll see in a little bit, there's some things that come out of that that are informative to us to understanding how different elements behave. Okay, if you look at the periodic table, usually it's expressed like in this picture here, where in the middle you have the atomic symbol. Anyone remember what K is? Potassium, great. Up on top is the atomic number. What does the atomic number tell us? Tells us the number of protons. And then atomic weight at the bottom, that's the mass. So that's the sum of what? If it's the mass, what does that equal? Let me put it another way. If the atomic weight is 39 and the atomic number is 19, how many neutrons does that have? Does anybody know?
20.
20, right. Because remember, the weight is the sum of the protons and the neutrons. And atomic number, that would be protons. So 39 minus 19 would be 20. So when we talk about the periodic table, The rows are called periods. So you see on the left there, 1, 2, 3, 4, 5, 6, 7. So that those would be called the periods. The columns are called groups. And in this one, you see it's 1A, 2A, 3B on down the line. And then you kind of go over there and then you get to 3A, 4A on down the line. Elements in the same group. So in other words, elements in the same column tend to have similar chemical properties. And so, you know, if we look at like lithium, sodium, potassium, that 1A group, those all kind of behave very similarly. And so one of the nice things about the periodic table is we can get information about ionization and different things like that and just various chemical properties just by looking at the table and kind of seeing what group they're in. The other thing that we will see, we'll learn, is that as you go across the rows, across the periods, you'll see trends as well, like increasing or decreasing trends as well about some properties. So the periodic table is pretty useful in trying to get an initial feel for how something will behave. For instance, maybe I understand sodium, number 11, really well, but potassium I'm not as certain about. Well, what I know about sodium is probably going to translate to potassium. So it's kind of a little bit of a cheat sheet, I think, of where rather than me having to learn every one of those elements, I can kind of get a feel for the different columns, the different groups, and then be able to understand how those are going to behave. And that's what we're talking about here, periodicity. They have this, the slide's kind of funny in the top, but if you look at the ones they're pointing out, so helium, neon, on down the line, those are the noble gases, and we see those are over there on the right, the far right-hand side. So all of those are the same column, the same group. So they're going to behave similarly. And that's this periodicity that they talk about, is that you get these kind of things going on. So for the helium in those are non-reactive gases. They're all non-reactive gases. What's non-reactive gas mean? Like right now, I'm not getting any reaction at all. It means nothing's going on. Those gases are pretty inert. They don't react much. They're saying lithium, sodium, potassium, that 1A group, soft reactive metal. That tells me that those are much more reactive. That everything in that column will react pretty easily. There are some common names for some of the groups. 1A is called the alkali metals. 2A, alkaline earth metals. To be honest, 6A you don't do much with. 7A, the halogens. That's pretty important one. And then 8A is the noble gases. So 1A, 2A, you often hear people calling things alkali metals or alkaline earth metals. That's pretty common. The 7A, 8A, halogens, that's pretty common, and noble gases in 8A. The 6A ones, to be honest, other than, oxygen and sulfur are used a fair amount, but I don't think I've ever called them the chalcogens or however you say that in my life. But those are some common names that have been assigned to these. Okay, I think we're going to stop there for today before we get into this next. Are there any questions about the stuff today or about the quiz? Okay, if not, thank you. We'll see you on Wednesday. Wednesday, we will have continued lecture on chapter 2, and then the second half will have the quiz. Okay? And for those of you in class, if you could just polite and write down, I'd appreciate it. Thank you.